Hello and welcome to the section of the chemistry tutor. In this section we're going to continue where we just ended in the last section, talking about mass percent composition, and this time we're going to dive and take this discussion a little bit closer to what we call empirical formulas in chemistry. Now in the volume 1 of the chemistry tutor, we've actually discussed the definition of what the empirical formula of a compound is and how it relates to the molecular formula. But just to give you a little bit of a refresher in case you've forgotten, basically the molecular formula is reality. That's what really exists out there. If you could zoom in on an atom or on a molecule of something, that would be the numbers and the subscripts there in that molecular formula would really be what's built in that molecule, right? But the empirical formula is basically the lowest, what am I trying to say? The lowest and smallest ratio that you can have between elements. So it may not be reality, but it does accurately reflect the ratio of the different elements. Let me give you an example of that to solidify that so that you can really understand what this is. All right, so a molecular formula for hydrogen peroxide, something that you know about, so you have it in your medicine cabinet, is H2O2. This is hydrogen peroxide, right? So if you could zoom in, if you could take your bottle of peroxide and open it up, pour it out and get a microscope and get really close up on it, you would see that it's 2 atoms of hydrogen and 2 atoms of oxygen. That's really what's bound into the molecular form, right? But the empirical formula would not be H2O2, it would just be HO. Okay, so the empirical formula is basically the smallest ratio of the atoms in there. So you see here I have H2O2. So what this basically says is that for every 2 atoms of hydrogen, I have 2 atoms of oxygen. And that's what's really bound in the molecule. But ratio-wise, 2 to 2, which means 2 hydrogen to 2 oxygen, is really the same ratio as 1 to 1. Yeah, I can have 2 red peanut M&Ms and 2 yellow peanut butter M&Ms, and I can say the ratio is 2 to 2. But we all know that that same ratio of 2 to 2 is also 1 to 1. It just means that for every red one, I also have a yellow one. For every 2 red ones, I have 2 yellow ones, right? So that's the difference. This guy is really how they're bound. The empirical formula is just when you take these subscripts, and if you can divide them by some number, where that you can divide everything in the compound by the same number and get something reduced, that's empirical. It's like simplifying a fraction. You know that 4/2, or let's say 2/4 is 1/2, because you were taught a long time ago that you look at the fraction and you say, hey, can I divide top and bottom by some number to give me a reduced fraction? Well, I can divide top by 2, giving me that. I can divide the bottom by 2, giving me that. Well, when I look at this, it's the same thing. I can divide this by 2, giving me 1. I can divide this by 2, giving me 1. So this is sort of simplified. So you can think of the empirical formula as like simplified, like you simplify a fraction almost, right? Why do we care about empirical formulas? Well, why do you care? I mean, if this is reality, and this is what we always use in our chemical, in our real discussions of like chemical reactions, and when we calculate mass percent composition, all that stuff, we're going to be using the molecular formula. But why do we care about the empirical formula? The reason is because if you discover a new compound in nature, something that's never been observed before, and you have absolutely no idea what the actual formula is, then what you're going to do is you're going to shovel a spoonful of this unknown material into your mass spectrometer, which is going to shoot a bunch of beams at it and get stuff that bounces off, and everything's going to be analyzed, and you'll get 39% carbon, 42% of this, 39% of that. And from that information, just by the percentages, you'll be able to construct the empirical formula. Empirical means to obtain or to learn by measurement. When something's empirically done, it means you do it because you observe it, or you do it because you look at something and then you figure it out. So that's what we're doing. It's by experiment, in other words. If we do an experiment, we get the mass compositions, we can easily find the empirical formula. We're going to do problems here in just a minute to show you how to do that, but that's why it's important. Once you have the empirical formula, then by definition, the molecular formula is going to be a multiple of the empirical formula. So like this guy, this molecular formula is just 2 times the empirical formula. And so basically what you do in real life is you shovel the thing in there, you get the mass percent compositions, you find the empirical formula, and that's the true ratio of all the elements to one another in the molecule. To find how the thing is really constructed, it might be a multiple of that empirical formula. And that's what we're going to be doing in these problems. So I wanted to give you a little bit of background so you kind of know where we're going with this before we really get there. So let's do the first problem. The empirical formula of a substance C3H2Cl, so 3 atoms of carbon, 2 atoms of hydrogen, 1 atom of chlorine, that's the empirical formula that we've measured, that we've somehow obtained. Okay? The molecular mass of this compound, is 147 atomic mass units. What is the molecular formula? So you see you're given two things and you're asked for a third. You're given the empirical formula, you're given the molecular mass, and you're trying to find the molecular formula. So the crucial thing to remember is that the molecular formula is always going to be some multiple of the empirical formula. It might be multiplied by 2, might be multiplied by 3. So all we have to do is use the information in this problem to figure out what that multiple is. And then we can calculate the answer. Because we know that the empirical, for this problem, the empirical formula is C3H2Cl. So this is the empirical formula. This is what we've gotten from experiments. These subscripts are reduced 3, 2, 1. You can't reduce it any further. You can't divide them all by something to make them any simpler. It's already in simplest form, really. But you know that the molecular formula is going to be some multiple of this. It might be multiplied by 1, in which case they will be the same, or you might need to multiply these subscripts all by 2, or you might need to multiply all these subscripts by 3, or all by 4, or all by 5. But you don't know what, but you definitely know that the molecular formula is going to be multiplied, taking this formula and multiplying it by some whole number multiple. How do we find that whole number multiple? Well, they give you a crucial a clue, because we know that the molecular formula, or I should say the molecular mass, is 147 atomic mass units. And you guys need to be savvy enough to know, now that we've talked about that, was when you have atomic mass units, it's the same thing as saying 147 grams per mole. Right? This is the molecular mass. So we're given the empirical formula, but we are also given the molecular mass. So let me ask you this. What can we find from this? Well, we know the empirical formula. If we calculate the mass of this compound here, then we'll have the empirical mass. So then we'll know how massive the empirical formula is. We'll also know how massive the molecular formula is. And we'll be able to look at those two numbers and figure out what the multiple is between them in terms of mass. And then we have our number to apply to this guy. So let's find the mass of this guy right here. So we need to find the mass, of the empirical formula C3H2Cl, which we've been doing all along. And see, this is why it ties into the material that we've been discussing just a little while ago. So the way to do it, we have 3 carbons. Each carbon is 12.011 grams per mole, right? We also have 2 hydrogens. Each one of those is 1.008 grams per mole. And each chlorine, we have only one of them, so it's 35.453 grams per mole. So when we do this multiplication, 3 times the 12 here, we're going to get 36.033. When we do this guy, we're going to get 2.016. And then this guy stays the same, 35.453. So when we add everything together, this plus this plus this, what we get is for C3H2Cl, what we get is 73.502 grams per mole. All right, so we've used what the problem gave us to find the molar mass, grams per mole, of the empirical formula. So we have the mass of this. We also have the mass of the molecular formula. So what is the multiple here? So if we just look at this guy and we say, all right, this guy, the molecular one, has a mass of 147 grams per mole. The empirical one has a mass of 73.502. When you take these and divide them in your calculator, it's going to be 1.9999, which is basically for all these calculations, this is so close, we're just going to say it's a factor of 2 bigger. So what we have learned here is that this molecular, whatever the molecular formula is, it's basically twice as massive as the empirical formula. So what that means is that we take our empirical formula and we multiply each little subscript by 2. Because that's what we've learned. We've learned that the molecular guy is twice as massive as the empirical guy. So we have to basically write times 2. So to actually do that, we take the empirical formula, C3H2Cl. This is the empirical guy, and we multiply every subscript times 2. So 3 times 2 is 6. 2 times 2 is 4. Chlorine times 1 times 2 is 2, Cl2. This guy is the molecular formula. Right? C6H4Cl2 molecular formula. So this is very important because this is going to be sort of a bulletproof thing that you'll almost be guaranteed to be asked on your test as well. If you're given the empirical formula for something and asked to find the molecular formula, all you have to do is find out what this multiplier is, because the molecular formula is always going to be some multiple of the empirical formula. You just have to find out what the multiple is. In this case, we calculated the mass of the empirical formula and got this guy, grams per mole. We were already given the mass of the molecular guy. They're a factor of 2 bigger, so then we just take and multiply each subscript times 2, and that's really all we do. And the rest of these problems are going to basically have a similar theme. Slightly different wording, make you think a little bit differently, but basically that's what you're going to have to do if you're trying to go from empirical to molecular or vice versa. So the next problem says a painkiller has a mass percent composition of the following elements. Carbon is 72.22%, hydrogen is 7.07%, nitrogen is 4.68%, and oxygen is 16.3%. Question is, what is the empirical formula? So here we're not asked for the molecular formula, we're actually asked for the empirical formula. And this is exactly what I was telling you before we did this problem, is that if you dig up some random material that's never been studied before and you stick it in a mass spectrometer, what you're going to get back is the percentage of everything in there. That's what we're given in this problem. Carbon, hydrogen, nitrogen, oxygen. We know what the percentage is. What is the empirical formula? Empirical means we put it together by measurement. We observe it, we put the lowest ratio of everything together. Now, you might be tempted to look and say, well, 72% of carbon, so I'm going to build the ratios based directly on these percentages. But you can't do that because even though the percentages are important, the masses of all of these elements are totally different. So you can't just go by the percentages. You have to find some common ground here. So what we're going to do, and what I want you to do for every problem that you have, is that this is just going to make it easier. Assume, this is even going to go under the class of a little bit of a mental trick for you to help you out. So make sure you understand this. Assume you have a 100-gram sample of this stuff. So it doesn't tell you how big your sample is at all. It just tells you the percentages. But if you assume you have a 100-gram sample, then you can immediately read off that if you had a 100-gram sample, then for carbon, you would actually have 72.22 grams of the carbon out of 100 grams. For the hydrogen, you would have 7.07 grams. For the nitrogen, you would have 4.68 grams. And for the oxygen, you would have the 16.3 grams. So you see, assuming that you have a 100-gram sample allows you to apply these percentages super easy. If you picked a 55-gram sample, then you'd have to do a bunch of multiplication to get to this point. But if you just pick an easy number, then you can easily have some grams to work with. Okay, because ultimately that's what we're going to be doing. Now, knowing that in this 100-gram sample I have this many grams of each of the elements, what we need to do is find out how many moles of every one of these guys, and that is going to be how we build our subscripts in our empirical formula. So for carbon, you have 72.22 grams of carbon. To convert it to moles, you just look at the molar mass in the periodic table. For carbon, it's 12.011 grams per mole. So we write 12.011 grams per mole. Grams cancels with grams. This is, again, the power of the unit conversion. I don't have to think about, should I divide by or multiply? I just put my grams, grams per mole. I could flip this guy over and put the 12.011 on the top, but nothing would cancel and I wouldn't actually get what I want. This way, grams cancels with grams. So in this many grams of carbon, I actually have, when I take this, multiply by 1, divide by this, I have 6.01 moles of carbon. All right? So it means if I shovel 100 grams of the sample out, I've actually got 6.01 moles. We've talked about what a mole is before. Each and every mole is 6.02 times 10 to the 23rd, in this case, atoms of carbon. All right, so this is how many moles we have. Now let's go on and do hydrogen, the next guy on our list. We have 7.07 grams of hydrogen. To convert it to moles, we say, well, each mole is 1.008 grams per mole. Grams, of course, cancels with grams, and so what I'm left with, take 7.07, divide by this guy, you get 7.01 moles of hydrogen. Okay? Now, the next guy is nitrogen. So for nitrogen, we have 4.68 grams of nitrogen. How many moles do we have there? So for every mole of nitrogen, we have 14.007 grams per mole. This comes right off the periodic table. And of course you're doing it that way so grams will cancel with grams. And then what you have, when you take this guy divided by this guy, you'll get 0.33 moles of nitrogen. And then the final guy is going to be the oxygen. For oxygen, we had in our sample 16.3 grams of oxygen. How do we convert to moles? On the periodic table, it's 15.99 grams per mole. Grams cancels with grams, so it's the same thing. 16.3 divided by this is going to give me 1.02 moles of oxygen. Now here's what we do, folks. When you build an empirical formula and you're trying to find those subscripts for your empirical formula, you don't put percentages down there in those subscripts, and you don't put grams down in those subscripts. You're putting moles down in those subscripts, because moles are ultimately measuring how many atoms that you have, right? Because don't forget, that's what a mole is. It's 6.02 times 10 to the 23rd atoms of something. So what this means is that in this sample, I've got 6.01 moles of carbon. So 6.01 times 6.02 times 10 to the 23rd atoms of carbon. This is basically indirectly telling me how many atoms of oxygen I have. This is basically telling me how many atoms of nitrogen I have. This is basically telling me how many atoms of oxygen I have. The number of atoms and the ratio between the number of atoms is really what your formula is. It's not mass. Those little subscripts are not related to mass. Those subscripts are related to how many atoms I have. So when you build your empirical formula, you have to put some numbers down there that are going to represent how many atoms I have. That's why we had to convert everything to moles. So to build the answer is actually pretty easy. You use these ratios and you do it like this. Carbon, you just write down exactly the number you have, 6.01 moles. Hydrogen, 7.01 moles. Nitrogen, 0.33 moles. And oxygen, 1.02 moles. Now, what this is saying is that this guy forms this compound in the ratio of 6.01 of carbon to 7.01 of hydrogen to 0.33 of nitrogen to 1.02 of oxygen. But you know that you don't have decimals for these subscripts. We don't want decimals. We want whole numbers. So what you need to do, especially, I mean, this is pretty close to 6 within a rounding error. This is pretty close to 7 within a rounding error. This is pretty close to 1 within a rounding error. I'm willing to accept that. But this is so far away from a whole number, there's no way it's correct. So remember what you've done. You've calculated this, you found the ratios. The ratios are what is important. Now, you can feel free to multiply this whole thing by whatever number you want to give you whole numbers in the end. Okay? So if I take 0.33, which is a third, and I multiply by 3, I should get 1. I'll say that again. This is basically 1/3, 0.33. If I multiply this by 3, then I will have a 1 here. But if I multiply this by 3, I have to multiply everything else by 3. So what we're going to have is carbon. When I multiply this by 3, it'll be 18.03. Hydrogen, when I multiply this by 3, it'll be 21.03. Nitrogen will be 0.99. Oxygen will be 3.06. And then basically when you get down to this point in your problem, you look at what you have and you say, These little decimals, they don't even matter because they're in the rounding noise. So you have carbon 18, hydrogen 21, nitrogen 1, oxygen 3. This is the empirical formula. Notice it is in lowest terms. You cannot, and I say N1 here, you don't have to put a 1 for any of these chemical formulas. If it's 1, you just delete it. There's nothing you can divide everybody by to make it any simpler than it is because you already have a 1 here. You have a 3 here. So you can't divide, you can't go and simplify it anymore. So just to recap, when you're given these percentages and say, hey, what's the empirical formula? Then assume you have a 100-gram sample. That just saves you a step because you can write the grams down. You can write the grams down accordingly. Now you don't have to pick a 100-gram sample, but if you don't, you're going to have to do another calculation to find out how many grams of everything you have. So take it from me, start with a 100-gram sample, write these guys down, convert every one of them to how many moles you would have. The ratio of these moles basically is the ratio in your chemical formula, in your empirical formula. But you want to get rid of decimals, so you multiply everything by something to get rid of it. So we multiply by 3 to make this as close to 1 as we can. When we do it, we say, okay, this is a rounding error everywhere, and we just go ahead and write it like this. So it's very common to get little decimals at the end, and then you just toss it off. Now, if one of these guys is grossly far away from a whole number, you've made a mistake somewhere. Like if we did all of this and this came out to 18.5, 18 and a half, then I made a big mistake somewhere. But 18.03, if I go back through and carry enough decimals everywhere, then I'm going to basically improve this guy so it's going to be so close to 18 it won't matter. So that is how you do that. And that is how you find the empirical formula in real life. Now remember, the empirical formula, it might not actually be built 18 atoms of this to 21 atoms of hydrogen to 1 atom of this to 3 atoms of this, because this is empirical. This is based on what we've measured, based on the percentages of everything. The actual structure of the molecule might be 2 times this. Maybe we'll have 6 atoms of oxygen and 2 atoms of nitrogen and 42, let's say, atoms of hydrogen and so on. Maybe it's multiplied by 3, maybe it's multiplied by 5, whatever. The actual molecular formula is a multiple of this empirical formula. But that's not what we were asked for. We were asked to provide the empirical formula. That's exactly what we found. Okay, so our last problem, we're just going to continue to work with what we've been doing so far, take it one step further, a little bit different, but same basic idea. A compound is 65.44% carbon, 5.49% hydrogen, 29.06% of oxygen by mass. Its molecular mass is 110 atomic mass units. What is the molecular formula? So you see, this is almost like what we did before, but we have an extra step. Because if you look back before, we were given the empirical formula, we were given the molecular mass, and we calculated the molecular formula. In this case, we are not given the empirical formula at all. We're given a bunch of percentages, and we're told to find the molecular formula. So you need to know, based on what we're doing here, what you know how to calculate. We're given the mass percentages, so we can find the empirical formula, right? From that and from the rest of the information in the problem, we can figure out that multiple and then find out what the molecular formula is. So we're kind of combining elements of both of these previous problems into one mega problem here, so to speak, if you understand where I'm coming from. So, again, we're going to find this empirical formula first. So take or assume a 100-gram sample, okay, of this stuff, just like we did last time. So what it means is, what we're going to have for carbon is if I have 100 grams, so carbon, the percentage was 65.44%. That means I'm going to have 65.44 grams of carbon. But I know from the last problem that ultimately I want to get to how many moles of carbon I have, because that's going to be those subscripts that I'm dealing with. So let me take the grams of carbon in this sample and convert it to moles. So what I'll do is I'll say, well, 1 mole of this stuff on the periodic table is 12.011 grams, so grams per mole. Grams cancels with grams. So what I'm left with when I do this multiplication and this division is 5.45 moles of carbon. All right, next, let's look at the next guy, 5.49% of hydrogen. So 5.49 grams of hydrogen in a 100-gram sample. All right? And I'm going to convert to moles. So 1 mole is 1.008 grams. Okay? So when I take this, obviously grams cancels with grams, multiply and divide, what I'm going to get is 5.45 moles of hydrogen. Okay? Now let's move on down the list and say, okay, the last thing I was given was for oxygen was 29.06% of oxygen, but since I'm dealing with a 100-gram sample, that's going to be 29.06 grams of oxygen. Let's convert it to moles. 1 mole of oxygen is 15.99 grams of oxygen. So the grams cancels with the grams. And when I do this multiplication and this division, what I'm going to get is 1.82 moles of oxygen. So let's take stock of where we're at. We know that this compound has percent mass of 65.44% of carbon, 5.49% of hydrogen, and 29.06% of oxygen. We put them in terms of grams because we're assuming we have a 100-gram sample. That just makes it easy. Then we convert everything to moles. The only reason we do this is so we can figure out what the ratio of the moles is to everything. 5.45 moles of carbon for every 5.45 moles of hydrogen for every 1.82 moles of oxygen. That is the sort of like the molecular ratio of everything. So we're going to use this to just construct our empirical formula straight away. So the empirical formula, which is not what the problem asked us to do, but you have to sort of map a path to the end, is C 5.45, H 5.45, O 1.82. And really and truly, this is the formula. I mean, this is telling you the ratio in moles, or in terms of atoms, from one to the other. Now, when you think about it on an atomic scale, yeah, you can't have 5.45 of an atom. So you want to get these things to whole numbers, the smallest whole number ratio you can. And it's up to you to basically multiply this guy, every element here, by some number. It doesn't matter what number you pick, but by something, so that every one of these guys will be a whole number. All right? So you got to play around with this a little bit. I mean, if you start multiplying by 1, or multiplying by 2, or multiplying by 3, or multiplying by 4, you're going to quickly find out, and you should try it. When you start multiplying all of these things by 1, 2, 3, 4, 5, 6, 7, you're never going to get them to line up where you have whole numbers for your empirical formula. It just doesn't work. So, and this is an example that's a little bit different from the last time. Last time we got down to this point and it was pretty easy. We multiplied by 3, this is going to make it 1. These guys are going to still be whole numbers, and we're done. Here, we try to do the same thing, multiplying by a whole number, and we're going to get nowhere, because you'll just see that when you do it. So don't forget, when I say you can multiply by a number, you can also divide by something as well. If you grab a calculator and divide this whole thing by 1.82, then this guy, you'll agree, will go to 1. But when you do this, it might surprise you. This will go to a whole number as well, and this will go to a whole number as well. So if you actually do that, you'll get carbon 3, hydrogen 3, oxygen 1. I'm just going to leave it as a 1. So what we've basically done is, it's just like simplifying a fraction, right? So like 4/8. We divide the top by 4, we divide the bottom by 4. We get a simplified thing. So we're doing the same thing here. We're dividing this by 1.82. That just gives us 1. And we do it on a hunch. We say, well, let's do that and see what happens. When we divide this by 1.82, it turns out that we also get a whole number. Same thing here. So bada boom, we're done. And it's not something you can see ahead of time. You have to play with it. You have to play with it to see, because your first instinct is going to start to multiply these guys by a number. But it's quickly going to get you nowhere. So if you can't multiply to get a number, then start dividing by some numbers that work. And so you finally hit one that does. But there should be, for every one of these problems, when you find an empirical formula, there should be a whole number ratio that's the smallest whole number ratio you can find. Okay, so let me go ahead and just leave this guy on the board. Now, we found the empirical formula, right, which is C3H3O. That is not what we're trying to find. We're trying to find the molecular formula. So we're given, now it's basically back to one of the previous problems. We're given the molecular mass, 110 in this case, atomic mass units. What we need to do is find out what the mass of this guy is so we can find the ratio of empirical to molecular. And because remember, the molecular formula is going to be some multiple of this empirical formula. It will definitely be some whole number ratio of it. It might be 1. It might be exactly the same as this, or it might be multiplying by 2 or by 3 or something else. So we have to figure out what that ratio is. The only way we can do that is to use the rest of the information on the problem. Molecular mass is 110 atomic mass units. What is the mass of this guy? Okay, so to find the mass of that, it's basically the same as we've been doing before. So for this guy, the mass is basically going to be equal to, it's going to be 3 times the mass of the carbon, which is 12.011, plus 3 times the mass of hydrogen, which is 1.008, plus 1 times the mass of oxygen, which is 15.99. All right, so the mass, when you multiply all this stuff out and then do the addition, what you're going to get is 55.05 grams per mole. All right, so this is for the empirical formula. This is for the empirical. Now we're given mass of molecular formula is equal to, what do we get here? 110. 110 atomic mass units, which is 110 grams per mole. They're the same thing. So you look at this and you say, well, the mass of this guy is 55 and some change. Mass of this guy is 110 and some change. That looks like double, doesn't it? If you take 110 divided by 55.05, it's going to be very, very, very close to 2. It's going to be 1.99999 something. So if you do that, if you say, all right, 110 for the molecular mass, 55.05 for the empirical mass, you're going to get 1.9999, which is so close to 2, it's just equal to 2. So what we found is the ratio of the molecular mass to the empirical mass is 2. So we take our empirical formula and we multiply everything by 2. So that means that we'll have C6H6O2. And this is the molecular formula. C6H6O2. I want to recap that real quick. So we start with some percentages. We assume that there's so many grams because we take a 100-gram sample. We convert them to moles. We construct the empirical formula. This is the ratio of everything as we have measured in the laboratory. We want to find whole numbers. We can multiply or divide this empirical formula, the subscripts here, by any number we want to try in an effort to get whole numbers that are of the lowest form. So we start multiplying and doing things, and we realize, well, if you just divide by this, it turns out to give nice whole numbers, so we do that. This is the empirical formula. Next, we calculate the mass of this guy. This is the empirical mass. And we notice that when we divide the molecular mass by the empirical mass, it's a factor of 2. So that means that it's measured in the lab based on these percentages of what's abundant, we get this. But the actual way that nature has constructed this molecule is actually double the amount here. Because even though it's built this way, the ratio of element to element is the same as the ratio element to element here. And that's what we measure. When we measure percentage of something, we're just measuring the raw ratios. But nature actually constructs it in a fashion that's basically multiplied by 2. Molecular formula is always going to be some multiple of the empirical formula. Well, that's all I have for this section. It's a lot of material. You're basically guaranteed to be asked this stuff on a quiz or an exam. And if not there, then definitely on your homework. So make sure you understand how to do it. I think I've given you some good problems, tried to give you some tips on what it all means and boil it down to you, for you so that you can take it away and do well in your homework. Make sure you can work these problems yourself. Even if you've seen them worked, go watch this video again, pause it, work these problems out, right? Make sure that you know how to do it. And then work extra problems in your book to get your practice up. And that way, when you get on your test, you won't be stressed out or nervous. You'll know, hey, molecular formula is just a multiple of empirical formula. You'll know, hey, when I want to find the mass percent composition, this is what I do. I've done it so many times. That way, you won't be stressed out. And if you can eliminate the stress on your test, then you'll do just fine. That's just the way it is. I'm Jason with Math Tutor DVD. Practice this stuff, and I know that you'll get good at it, and you'll do very well.